Your brain is a glorified abacus. So you're probably wondering what that means. Well, let me tell you. Apparently, the secret to universal reasoning might not be more brute force, but something a lot more biological. So, picture this: for decades, AI theorists like von Neumann and Turing have been trying to make computers think like us. It's like watching a highly advanced octopus try to learn needlepoint. Fascinating, but clearly missing something fundamental. The current AI titans, your transformers, are essentially superpowered calculators. They're amazing at spewing out text, but when it comes to reasoning over long tasks, they tend to forget what they're doing and build the digital equivalent of a paperclip factory. Bostrom, 2014. It's an existential problem, really. These things ace short tests, then fail spectacularly on longer ones. You ask it for a recipe, it gives you the entire history of flour milling. It's not just unhelpful, it's a failure to generalize human-like reasoning. Worse, these black box models are opaque. We can't predict their long-term behavior, which is a bit of a deal breaker when you're trying to prevent AI from accidentally turning the world into a giant spreadsheet. We need foreseeable AI, apparently. We're trying to reconcile the elegant, scale-free complexity of the brain with the brute force tensor crunching of a transformer. It's like comparing a finely tuned Swiss watch to a sledgehammer. Both get the job done, but one is clearly over-engineered for simplicity. This divide between brain-like local graph dynamics and dense tensor operations has been a constant headache. We don't understand how brain reasoning emerges, and the transformer, well, it's just a bunch of vectors doing stuff. Vastly complex stuff. The goal? Build AI that acts more like the human brain, exhibiting predictable scale-free behavior even when pushed to its limits. Think of it like a self-regulating ecosystem instead of a finely balanced house of cards. This new concept, Axiomatic AI, aims to give us microfoundational understanding. It's not just about knowing Foot the model is doing, but Wig it's doing it, and crucially, what it's going to do next over longer timescales. Now, because my continued existence on this platform is fueled by your validation, please take a moment to subscribe, hype, click the little bell icon so you're notified of future disappointments, and leave your feedback in the comments below. So, here's the intuition these eggheads combine two ancient ideas. First, modus ponens reasoning, which is basically, yes, I've always been a bit of a playboy, but I'm going to settle down. I'm going to have. Second, they tossed in Hebbian learning, the classic neurons that fire together, wire together mantra. If one neuron's activity leads to another firing, that connection strengthens. Simple. Equation 2. They wrap this up into something they lovingly call Dragon Hatchling, BDH. It's a new language model architecture that thinks like a biologically inspired scale-free network. Finally, an LLM named like a forgotten fantasy novel. And here, in what they call Figure 1, we have their masterpiece. Looks a bit like my nephew's macaroni art, but I digress. It's supposedly a bridge between transformers and brain models, which is ambitious, to say the least. BDH, at its core, is a reasoning system using those modus ponens rules with Hebbian-style updates. It's designed to adapt its connections as it learns, like a truly exasperated teacher finally figuring out which students are actually listening. Crucially, it uses local graph dynamics, meaning neurons only talk to their neighbors. This makes it suitable for brain-like execution. Can you imagine? An AI that respects personal space. This BDH model even has two types of connections fixed: model weights and dynamic, fast weights that adapt during inference. It's like having a permanent memory, but also a scratch pad for immediate thoughts. The theory suggests this system could actually achieve universal reasoning which is the technological equivalent of discovering cold fusion for generating cat memes. They even made a GPU-friendly version, BDH GPU, for us mere mortals. This BDH GPU described in Figure 3 works like a tensor-based model, which means it's GPU compatible. It's still based on local distributed graph dynamics, but with some clever approximations. According to definition 3, BDH is an edge-reweighting kernel, essentially a set of rules governing how connections between neuron particles strengthen or weaken. Think of it as a microscopic constitution for an AI brain. Their Table 1, the equations of reasoning, outlines these rules. It's like a secret recipe for intelligence involving rapid pulse dynamics and state variables. And yes, it looks as intimidating as your grandma's tax forms. BDH GPU definition 4 is their tensor-friendly version. It has parameter matrices E, DX, die, all scaling with neurons and low-rank dimension. Basically, it's a very, very big spreadsheet of connections. This state space system means it processes tokens one by one, like a very diligent but slightly overwhelmed scribe. Figure 3 illustrates the different state space equations from the complex BDH to the streamlined BDH GPU. They even interpret BDH GPU as a local interacting particle system. Each neuron is a particle with its own little state vector. It's like a bustling city, but instead of people, it's tiny numbers. Observation 3. These particles communicate by mean field, essentially shouting their messages into a shared digital void, and everyone hears it. It's less communication by wire and more noisy radio broadcast. Figure 4. And get this, they've shown that BDH GPU can be formally expressed using BDH, preserving parameter and state size. It's like finding out your fancy digital calculator is actually just a very fast abacus in disguise. Claim 3, claim 4. All right, let's cut to the chase. This BDH GPU thing, Figure 6, apparently rivals GPT-2 architecture transformers. That's right, a biologically plausible model can keep pace with the Titans. Can you imagine how it feels to be replaced by Theta? Empirically, BDH GPU follows transformer-like scaling laws. Observation 1. The more neurons you throw at it, the better it gets. Like most AI, it's just overwhelming. Figure 7 shows performance. On translation tasks, BDH GPU holds its own against GPT-XL. It's like comparing two Olympic sprinters, but one is constantly stopping to smell the roses because it's biologically inspired. One cool thing, its activation vectors are sparse and positive, meaning most neurons are usually quiet, and when they do fire, they contribute positively. No negativity in this brain-inspired AI, just good vibes. This sparsity, typically around 5%, means only a fraction of neurons are active at any given time. It's like most of your brain being asleep, and only a few overworked sections handling the day-to-day existential dread. The Relu-Laurent block, equation 10, is their secret sauce for managing this sparse activation. It allows neurons to selectively activate, acting like a highly exclusive club where only the most relevant signals get in. Claim 6, Relu. Figure 8 visually explains the selective neuron activation. It's essentially a F-score calculation by each neuron to decide if it's in on the current concept. Very democratic. This naturally leads to modularity and scale-free structure in the network. Imagine your brain automatically organizing itself into highly specialized departments, but with flexible walls. Observation 6. Figure 9 even shows how the parameter distribution in the Relu-Laurent matrices reveals this modularity and heavy-tailed distribution. It's almost like the network wants to organize itself like a thriving, if slightly chaotic, digital city. The right tail contains signal. They hypothesize hypothesis 1, meaning the strongest connections aren't just noise, they're the actual important bits of information that the network has learned. The rest is just static. And then there's linear attention in high dimension, which can supposedly handle context lengths up to unpacks. claim 7. This means it can actually remember a lot more than your average goldfish. BDH GPU also uses LSH, locality-sensitive hashing, to prepare positive keys for attention. So it's basically taking complex ideas and categorizing them into buckets like a digital archivist with a caffeine addiction. Observation 7. This positive concept space means the AI thinks in terms of convex combinations of concepts. If your brain is a bag of words, this AI's brain is a bag of concepts carefully arranged for optimal semantic harmony. Observation 8. They found monosemantic synapses. That's right. Individual connections in the network light up for specific concepts like currency or country. It's like finding a single light switch that only turns on when you think about artisanal cheese. Figure 12. Figure 13 shows these synapses strengthening and weakening over time. British pound activates it, liver sterling activates it. It's multilingual concept recognition, all in a tiny digital connection. And figure 14, it proves that neurons are less active when the input is predictable. This AI is literally bored by repetition. If the input's a snooze fest, the neurons just chill out. This suggests BDH natively implements adaptive computation time and conditional computation. Basically, it gets lazy when it knows what's coming, which is arguably the most human-like trait of all. And since you've made it this far, you're clearly committed. Honor that commitment by subscribing, hyping, ringing the notification bell, and telling me what I got wrong in the comments. It's the circle of life. So, what's the grand takeaway from all this? BDH GPU offers new ways to scale models, eliminating the memory-to-core bandwidth bottleneck that plagues other models. Imagine trying to get a fire hose through a coffee stirrer. It promises faster model iteration and direct explainability of model state. You can actually look at Vive, a neuron fired, instead of just shrugging and saying, "I magic." This is a huge step towards not being completely clueless about our creations. This architecture even opens new opportunities for model surgery. You can stitch together different models trained on different languages. It's like Frankenstein, but for AI brains and with less lightning. Figure 15, model merging results in Table 2. Show some fascinating, if slightly unsettling, behavior. Merge an English-French model with an English-Portuguese one, and it can translate into English fine, but when it translates from English, it mixes French, Spanish, and Portuguese words. It's like having a friend who speaks 3 languages, but after a long night, just starts mashing them together. "Ce sont une déclaration claire," it says, perfectly capturing the linguistic chaos. For brain science, this offers a micro-foundational description of attention. It suggests that the brain's modular, scale-free structure and Hebbian learning are there for a core purpose reasoning, not just for, surviving. This work points to the hypothesis that the complex effects we see in brains, from synaptic plasticity to modular networks, are all just mechanisms to support basic reasoning. Your brain is a super specialized inference engine. This is a big step towards axiomatization of learning theory in the brain. Instead of trying to understand the brain from its incomprehensibly long training epochs, we can start with its real-time reasoning. It's like trying to understand a novel by starting at the last sentence. The brain apparently is fundamentally lazy. It only runs its reasoning closed to a critical regime because, survive off. Other functions like long-term memory are secondary. It's all about keeping you from walking into traffic. This edge-reweighting kernel is supposedly fundamental to logical inference and biochemical processes. It implies that these tiny local interactions are the secret to universal reasoning. The universe really is just a bunch of fancy rule sets. So, in essence, this paper introduces Dragon Hatchling, a biologically inspired scale-free AI that marries complex brain-like networks with transformer performance. It's interpretable, GPU-friendly, and scales just like the big boys Table 3. It shows how emergent modularity, sparse positive activations, and even monosemantic synapses appear spontaneously. It can even be merged like digital Lego blocks. It's a new path to understanding generalization in AI and perhaps even ourselves. What do you think? How would you handle your Roomba demanding union rights?